Hey guys, my name is Jessica Halverson, and I will be doing our sorting and searching algorithms review for Programming 1. And I'd just like to mention that Shajeev Ghosh helped make these materials with me, but it'll just be me making the video. I'll be covering 5 sorting algorithms. We're going to do selection, insertion, bubble, quick, and merge sort, and we'll do 2 searching algorithms, linear and binary searches. So to start, we'll do selection sort, which is definitely the most straightforward. So basically, we start with this unsorted array, and you're just going through and picking the smallest element and bringing it to the front or the sorted region, if you want to say. Or if you're sorting not in ascending, if you're doing descending, then you'd go and find the largest and bring it to the front. Um, so the time complexity for this is O(n) squared. It's basically going to involve 2 for loops. You can have an inner and outer. Space complexity is 1. We don't need to make any new arrays or data structures. Um, so if we start here, we see 15, 22, 4, 8, 17. Obviously, the smallest is 4. So we're going to swap 4 and 15. And then you'll go through the whole array again, find the next smallest, which is 8. Do the same thing, swap 8 and 22. And then you'll kind of keep doing the same exact thing. So then 15 is already in its place, so no swap necessary. And then 17 and 22 will be your final swap. And then it's fully sorted. So that one doesn't take too much time to go over. Really straightforward. Um, Not the best idea time complexity wise, but if you're not super concerned about how long your program is going to take, you just want to do a simple sorting algorithm that's easy to implement, it's a good option. And then so next we'll have the insertion sort. So kind of a similar idea. Usually people like to explain this as like a sorted and unsorted portion of the array. So you'll pick each piece one by one, and then you'll put it into the sorted array in its correct location. So first you'll start and you'll take the first 2 elements and you'll compare those two. So I guess really like 15 would go in first. And since it's by itself, it's automatically in the right location. And then you'll pick 22. So look at 22, compare it with 15. And since 15 is larger than 22, it's going to go as the element after 15 in the sorted portion. And then after 22, you'd be looking at 4. So you'd compare 4 with 15. And since 4 is less than 15, or sorry, I did that backwards. First, you compare with 22. So since 22 is greater than 4, you're going to move 4 to the left of 22. And then after that, you're going to compare with 15. And since 15 is greater than 4, 4 is going to go in front of 15. And then you're going to look at 8 and do the same thing, kind of like a waterfall, moving it down. So since 8 is less than 22, it's going to go in front of 22. Then you're going to compare it with 15, and then you're going to compare it with 4, which is greater than. So it's not going to go in front of 4, and it's going to get placed in between 4 and 15. And like when I say you're moving it down, you wouldn't be actually placing this in the array at that point. It would more be looking at the pointers there and comparing the values until you find the index where you want to put it. So you wouldn't be doing like array at I equals 8 right now. Like you're going to keep checking and see what location it should go in and then finally write it in that location. Um, Okay, so we finished 8, and then we would do 22, and 22 is already greater than all of these, so it stays in place, no changes necessary. And then for 17, you would compare it with 22. Oh, wait, sorry, 22 is at the beginning, 17. 17 is less than 22, so it moves over once, greater than 15 stays where it is. So pretty straightforward again, nothing too complicated about this one. It's a very linear model, also going to be O(n) of n squared. You're going to have 2 for loops with 2 different pointers, and space complexity is 1. No new data structures need to be made. So yeah. Um, our next, a little bit more complex, but still fairly straightforward, is going to be the bubble sort. So the bubble sort, the way I think of it is like I always go like this with my fingers, like you're just flipping, 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 flipping down the line, and then you do the next pass, flipping, 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 until eventually everything is in the right place. So the time complexity for this is also O of n squared. That's the worst time complexity, I believe, also the average time complexity. Um, but so you'll start with your first two elements and compare them, and if the one on the left or is greater than the one on the right, or if you want to think about it the other way around, if right is less than the element on the left, you need to swap. So whichever way you want to implement it doesn't really matter. You just need the lesser element to be on the left and the greater one to be on the right. So if you look at 15 and 22, they're already sorted, so you don't need to do any swap. And then you're going to compare 22 and 4. And since 4 is less than 22, 4 is going to swap and be on the left side of 22. And then from here, you're going to compare 22 and 8. So since 8 is less than 22, 8 and 22 are going to swap places. And then 22 and 17, we're going to compare. Again, 17 is less than 22, so they're going to swap places. So you can see it's kind of like a cascading effect. The larger number is going to keep getting pushed higher and higher and higher. And these lower ones might not necessarily be sorted yet, but that's what the other passes are for. So this all counts as one pass. And so now the idea of this is the rightmost element will be sorted after each pass. So this 22 kept getting pushed along, and now the 22 is in its correct place. There's nothing greater than 22, or it would have had to be switched with it, which it wasn't, obviously. So then our second pass, we're going to start with the first two elements again, which are now 4 and 15, which again end up being sorted, so you don't need to do any swaps. And then you look at 15 and 8. 8 is less than 15, so 8 and 15 are going to switch. And then 15 and 17 already in place, so we don't need to worry about that, which means that 17 is now sorted, as we can see here. So then we'll do our third pass. So now we're comparing 4 and 8, which 4 and 8 are both in the right location. Then we check 8 and 15, which are also right in the location. So now 15 is sorted. And then we'll do the last two, 4 and 8, both sorted. So those are the final things we needed to check. And we can be done. We have our final sorted array. So you can see sometimes things will already be sorted. Like really after this first pass, it was pretty much sorted. We had one more switch to do. But obviously a computer doesn't know that. It's not looking at everything the way that we are. So you have to continue doing all of these swaps and verifying that everything's in the right place. So there's no way to like cut the time complexity because halfway through it was already sorted. Your computer doesn't know that, and that's not part of the algorithm. So then quicksort, this one I'm going to spend more time on and show you guys some pseudocode too, because this one can get confusing, at least in my opinion. So the big premise of the quicksort is that you pick a pivot point, and through that pivot point, you have a left and a right, or like a low and high pointer, whatever you want to call it. And based on the low and high values compared to the pivot, you're going to be swapping elements, swapping with the pivot, or continuing to move along. And this is a recursive algorithm usually. I'm actually not sure if you could implement it other way than recursion. That's definitely like the best way. And so you're going to be making all these smaller and smaller partitions, kind of similar to a merge sort, which we'll talk about in a little bit. But you'll get down to basically like one element, and then you're going to expand back out. So now, okay, now let me compare to the right and to the left and see what we need to do. So let's just start talking about it because that'll make it easier. It's confusing when you just say a bunch of words. Would also notice that the time complexity is lower. So n log n is less than n squared. So even though it's a little bit more confusing, if you're worried about time complexity, it is a better option than the other three that we've been over so far. Okay, so to start, you can pick your pivot point as any point. It can be the first element, the middle element, the last element, or any random element. It doesn't matter. But it's pretty standard for the last element to be picked. So that's the way that I wanted to show you guys. So if we have the same array that we've had this whole time, 17 is going to be our pivot because it's the last element. And then we need to pick a left and a right pointer. So your left pointer is going to be your leftmost element, and your right pointer is going to be your rightmost element, excluding the pivot. So from here, the way this algorithm works is our left pointer, we're going to continue to increment up one. So move it to the right until the left pointer is no longer less than the pivot. So if we look at 15, 15 is less than 17, so we're going to move it up to 22. But now 22 is not less than 17, so we're not going to increment it anymore, leaving it there. And then our high pointer, or our right pointer, is 8. 8 is less than 17, so it's not even going to move left once. It's not greater than 17. It's got nowhere to go. We're already in the position we want it to be. So now the algorithm says, okay, we haven't passed each other yet. The left and right pointers haven't passed each other yet, but they're both to their maximum point. The left pointer is finally to an element that's greater than the pivot, and the right pointer is to an element that's less than the pivot. So we're going to swap them. So here you'll see that this 22 now becomes 8, and this 8 now becomes 22. So from here, we're going to do the same thing. We keep doing this until our pointers cross or equal each other. So they haven't done that yet, right? So this is our low pointer. This is what it starts out. So 8 is less than 17, so we're going to move it right. 4 is less than 17, so we're going to move it right. So 22 is what our left pointer ends up as. And then our right pointer was originally this 8, or which turned into 22, right? So 22 is greater than 17, so we need to move left once. So 22 is greater than 17, move left. And then 4 is less than 17, so you're not going to move right. That's as far as it can go. But you'll notice now that these two pointers crossed. So now the left pointer is further along than the right pointer. So that indicates that we need to switch with the pivot. So our left pointer is going to switch with the pivot. So now if you look at this array, our pivot is located where 22 once was, and 22 is where 17 was. And so now our algorithm will say, okay, we found our new partition point, is what people like to call it. And so now we have a left array and we have a right array, both of which are unsorted at this point, and we need to sort them. So you'll see here that the way it gets split, and I'll show you guys the code for this after, which I think helps out a little bit, makes it a little less confusing. So now this array over here is basically its own thing. You're going to think of, you're not even going to consider anything on this right side of this thick line when we're sorting this left side. So now we're starting from the beginning, doing the same thing that we did up here. And so our pivot is the rightmost element, 4, and our left pointer is 15, our right pointer is 8. And so we're going to do the same thing. We're going to move around the same way we were moving before. So 15, if it was less than 4, we would move it to the right, but it's not. It's greater than 4, so it's staying where it is. But our right pointer is greater than 4, so it's going to jump to the left. And now it's at 15, which is our last element anyway, so it would have to stop there. But it is greater than 4, so theoretically it would keep moving, but it can't. So they're both at 15, which means, again, we have to do a switch. So you switch the left pointer again with the pivot. So we get 4 and 15 flopped. And so now our array is sorted. So I didn't put any more pictures on here just because the way this element, or the way this algorithm is illustrated, it would be hard to do that anyways. But basically now, recursively, what would happen is this 4, they would make a new partition, and the left side is nothing, so that's already sorted. And then the right side would be basically nothing too. And so then it's going to jump and it's going to go back and it's going to do this other side and it's going to sort that. So it says, or I kind of lied, the right side would be this 8 and 15. which so then it would jump to 8 and 15. It would do the same thing. And it would be like, okay, pivot is our last element, which is 15. Left and right are both 8 because that's the leftmost and the rightmost. So if you only have one element, it's already sorted. So you know that's already sorted. And then you come to this side because this was the right side from above. And you would do the same thing that we just did with 8 and 15. Okay, 22 is our pivot, 17 is our left and right. They've met each other. Do any switches that need to be done. So now I'm going to show you. We switch what I'm sharing. Okay, this code. So this is some pseudocode for the quicksort. And so usually you'll have two methods or functions, whatever you want to call them. So you have the quicksort, which is like the main thing that you would call. So if you had a main method and you had some array that you wanted to be sorted, then you would do quicksort with that array and you choose the leftmost, which would be 0, and then your right, which would be length -1. And so you'd put it into this. And so if right is less than or equal than left, so basically like if it's only one element or if you have no elements, you're done, then you're done, right? Return that portion. Now we're going to do the left or the right side, whatever. So you get your pivot, which we're choosing as the rightmost element, and then you'll partition with the left, right, and pivot. So wait, actually, I'm going to share my whole screen so you can see the whole thing next to each other. So let's move this to the side and this here. Okay. So pivot, so this is assigning our pivot to be 17. And then our partition point is going to equal whatever we get from this. So partition, so now we're calling this with left, right, and pivot. So left and right would be coming from this, which I said before was this first element and this last element. And pivot is also your right. A pivot is your right element, but it's not a pointer. So if you see these left and right pointers, they would be like indexes. So left would be 0 and right would be 1, 2, 3, 4. And pivot would be 17. Pivot is actually the value, not the location. So then we'd come up here and we say, okay, left pointer equals left, right pointer equals right -1, which is kind of unnecessary, but. And then while true, so we're going to keep doing a loop. We're going to keep doing a loop until we get to this point where we're going to break out. And this point is when the pointers either equal each other or pass each other. Like I said, that's the point where we know when we're done. We got to swap with the pivot. So you look at this and you say, okay, while left pointer is less than or equal to right. So what this is saying is basically while we haven't gotten to the end. And then while the left pointer is less than the pivot. So like I said, okay, we're less than the pivot, keep moving right, keep moving right, keep moving right until we get to the point where we're not supposed to go anymore. So then you do the same thing for the right pointer, and then you'll check if left pointer is greater than or equal to right pointer. Like I said, are we at a breaking point? If it's not, then we're going to swap the left and the right pointer. So what we did here, when we kept jumping, and then we said, okay, 22 is greater than 17, so we need to stop. And 8 is less than 17, we need to stop. So my left and my right pointers are not moving anymore, but they haven't passed each other yet. So what do? So I just swap. I'm going to swap the left and the right pointer, which we see happen here. 8 goes here, 22 goes here. And then you're going to jump back up. You haven't hit that break, so we got to keep going. So then you keep moving the left pointer, you keep moving the right pointer, but then this time they passed each other. And so now instead of swapping our left and right, we're going to break out of this while loop and we're going to swap the left pointer with the right, which is the pivot. And so this swap element is taking locations. So in there, you would just take like array left pointer equals array right pointer. Obviously, you need to make a temp in there so you don't lose any data, but very simple, just swapping the data at each of these left and right points. And then from there, we'll return the left pointer. So then you'll see, okay, so this is our partition point now, left pointer. So our left pointer, after we swapped, so what do we do? We swapped here, so we have 17 and 22. So our left pointer is pointing to 17 here, and that's our partition point now. So now we're going to do the quick sort on the left side. And so we're recalling here. So left is going to be this 17. And then, or sorry, no, that's partition point. Left is 0. Left is what we passed in at the very beginning. Left is this 15. And partition point is this 17 now. And so it's doing left and partition point minus 1. So that's why this line gets drawn here, because now we're doing quicksort with just these 3 elements. And so we get back up here. If right is less than or equal to left, it's not. We have multiple elements, but that's how at the end, when we only had this 4 left, or really nothing left on the other side, it knew to return. Okay, left is done. And then that would jump back out, and then it still has to do this right side because it's recursive, right? So it does the left, finishes this whole quicksort, but now it's got to execute this line. So you're gonna get this stack of things that need to execute. And eventually your whole thing will be sorted. So I think this one's kind of confusing. I think it's the most confusing. But hopefully I kind of explained that well. And I really do think the best way to understand it for yourself is to sit here with the code right in front of you and step through every single thing, even to the end when you get every single little recursive chunk of one thing on its own, step through it and show yourself how it works and that it really does work. It's just probably too time consuming to go through every single little recursive chunk. But you have this pseudocode now. You can look at this and this picture of the array, pause if you need to, and go through it. But now we're going to move on to merge sort. So let's make this big window. So merge sort is kind of the same idea. You're breaking it down into little chunks using recursion. But you don't have some like pivot point that you're flipping around and checking, and like there's not a whole lot of extra stuff. You're breaking down and you're putting back together. So they like to call this a divide and conquer technique. So same time complexity as the quicksort, you got the n log n. So the log n is always like a result of a division, like making something smaller. Like you'll see when we do binary search in a little bit, it's like you keep dividing it by 2, by 2, by 2, by 2. And that's how you get the log n. Okay, so let's look at this. So we have our unsorted array, and you're going to split it in half. So you're going to get 1/2, and obviously, if you have 5 elements, you're not going to have 2 halves that are the same thing. It doesn't matter if one has 3, one has 2. No worries. It's just going to depend how you choose to to split in half. Who gets that middle one? So then, as you see, it just keeps breaking down, breaking down. So then you have 15, 22, 4. Okay, break in half. Okay, so we have 15, 22, and then this 4 would be here. The 4 is already on its own, so it's done. You're gonna get down to single elements of every single thing. And then from there, you're gonna chunk back up. So then we're gonna look at 15 and 22. And we're going to sort them from there. So 15 and 22, 15 is less than 22. So we're going to put 15 in the array, and then we're going to put 22 into the array. And then we're going to say, okay, so we have 15 and 22. What was the other thing that broke off from that? Oh, it was the 4. So we're going to look at 15, 22, and 4. Okay, so now this is kind of similar to the insertion sort, where it's like, okay, I have this sorted portion and I have this unsorted portion, then I need to find where it belongs. So you're going to look at this 22. Okay, no, 4 is less than 22. Let's keep moving down. What about 15? 4 is less than 15. Keep moving down. So now you have 4, 15, and 22 all sorted. And now you're going to look at this other side. So on this side, and remember this is recursive, right? So this chunk expanded to this. So these two need to chunk back up. Sorry, I don't know why I keep using chunk. It's like kind of disgusting, but they need to go back together. And then once these two are back together, the program is going to know, okay, now these are the sides that need to be merged together. So these two are going to be merged before this can happen here. So 8 and 17 are going to look at each other. Okay, who's less than or greater than the other? Okay, 8 is less than 17, so 8 is going to go in the array, and 17 is going to go in the array. So you have 8 and 17. So then you're going to look at these two arrays, and you're going to have to take chunk elements from this one and put it in here, and then 17 and put it in here, put everything in the right order, and then you have your sorted array. So like I said at the beginning, divide and conquer, get everything to its smallest piece, and then gradually put everything back together. And so I'm going to show you code for this one too, because this one can also be a little confusing. It's also recursive. So I also think for this one, step through it like seriously for every single element, write it out on a piece of paper, keep track of what every single index is, what every single pointer is, and what your sorted array is, what unsorted array is. So same kind of idea. We have this recursive program. We have two functions. We have the merge sort and the merge. So merge is technically like the helper function, kind of like up here when we had quick sort and partitions, the helper function. But it's kind of funny to me because like the merge and the partition are like really doing the most work. And like the main function is just kind of telling everyone what to do. But anyways, so in your main, you would call merge sort with whatever array you need to sort. So if the length of array is 1 or 0, so again, this is where you're trying to get. You need to get everything down to 1. So once it's at 1, now you know, okay, we can start rebuilding. But until then, you need to divide by 2. All right, divide by 2, and then you'll do the left side. So then you'll call this again, merge sort 0 to mid. So then here, so we said mid divided by 2 is going to be this 4, maybe, yeah, this 4 or 8, one of those. And then you're going to take the left side, 15, 22, 4. And then what's going to happen since this is recursive, right? So this gets called, and now we're back up here with a new array. Okay, array is not less than or equal to 1. So let's go again. We got a new middle, which is 22. And then let's do our left and our right. So left, okay, well, we're calling merge sort again. So merge sort on the left. So now we got 15 and 22. Let's call it back up. Length of array is still not less than or equal to 1. So we get another middle, call left again. Now array is just 1. So when we come back up again, okay, array is less than or equal to 1, we can return that array. So we return 15 and we're back up here. So we're back to 15 and 22, but now we need to do the right. So now we call the right, we call merge sort on that, which gives us a length of 1. So then we can return that, and now we get to actually merge. So we have 15 and 22, and those need to be merged together. So our left is 15, our right is 22. And then your left index, your right index, which is just counting where you are at the time. So while left index is less than length of left, and right index, sorry, I can't talk, is less than length of right. So you're just making sure that you're not out of bounds. Look at their subarrays and merge. So if left at the left index, so if 15 is less than or equal to 22, then in our result array, we're going to append that left index. So we do. So 15 goes there. Okay, cool. Now we're going to be at the end of that thing. There's nothing else to do. But our right array still has an element in it. We haven't put it anywhere. So we're going to add the right array. And so now you have 15 and 22 together. And you're going to do that for all of these chunks. So then you'll get back up and you'll have to add this 4, you'll have to add these, and then you're going to have to do this whole right side where they add together. And finally, they'll all add together at the very end. So another one where it can just be confusing to visualize. Even with a picture like this, it's hard to think code-wise how it's figuring out to merge all this together. So again, pause the video, step through the code, write it down on a piece of paper, track every single step in your array at that step. Okay, so now we are gonna move on to searching algorithms. So honestly, I'm gonna start with the linear search just because it's super straightforward, really easy to figure out. It's very similar to the first sorting algorithm we did, the selection sort. Literally, you're skimming through and you're finding what you need to find. So let's look, linear search, best case, O of 1. That means the first element you check is your element that you want. But most of the time, it's going to be O of n. You might have to look through the whole list. So basically, okay, let's say we have this array and we have the indexes shown here too, just to help you visualize. And we want to find 53. All this algorithm is going to do, you're going to have a for loop, and all you're going to do is at every single index, you're going to say, does this element equal the element I'm looking for? So you check 2. Well, 2 doesn't equal 53. Let's check 7. 7 doesn't equal 53. And then you're going to check 13, 46, 53. Oh, okay, 53 equals 53. And whatever you want your program to do, if it wants to return that index, whatever you need to do, you found it, you can be done. So super straightforward, like I said, really nothing complicated or hard to understand, just a for loop checking every single element. But your binary search is kind of like the merge sort, but even simpler, really. You don't have to worry about combining anything back together. You're just throwing half of it away and never thinking about it again. Obviously, not like actually deleting it, but like not searching it anymore. So, same idea. Let's say we're looking for 53. So, what we're going to do is we're going to look at the middle element. So, middle element happens to be 46. So, at 46, is 46 less than or greater than 53? So then obviously we're going to say it's less than 46. Oh, and very important to mention, binary search has to be a sorted array. If it's not a sorted array, it is definitely not going to work. So it has to be sorted. Don't try to use it if it's not sorted. If you want to use it, you got to use one of these sorting algorithms that we just talked about. So 46 less than 53. So we're going to say, okay, well, 53 is greater than 46, and this array is sorted. I know that 53 cannot be at any indexes less than the index that 46 is at. So we're going to forget about 46 down. So here you see this is grayed out by. We don't need to worry about that. We're only going to think about the top 3. So now we have 53, and we're going to say, okay, from this chunk, what's our middle? Okay, well, 76 is our middle. Now, is 76 greater than or less than 53? And you're going to say 76 is greater than 53. So I don't need to worry about 76 or anything above it. And then you'll just be left with 53. So obviously this is a small array. So when you're dividing by 2, it's not going to take you very long to find it. If you have bigger arrays, it's going to take longer, but it's the same process. All you're doing, finding the middle, throwing out half, finding your next middle, throwing out that half. So pretty simple too when you think about it. Searching algorithms, pretty straightforward. Sorting algorithms definitely can take some time to understand. Really focus on this quick sort and merge sort if you find yourself confused. I know I'm not the best at explaining things, but it's hard to even just say it with words. You really need to write it out and visualize every single step that's happening to understand it. But yeah, I hope this was helpful and you do good on any quizzes or exams you need. Have a good day, guys.